Welcome back for another VMK in the Math series. In this VMK, I'll be describing how to generate the equations to create a smooth interpolation line. By now, you guys should be pretty familiar with linear interpolation. As a matter of fact, if you take a look inside of the Math series, the first VMK in the Math series was describing lines in 2D, which are linear interpolation, and in VMK number 5, I used lines to map values between one range to another. In this VMK, I'll be taking this a step further and showing you how to not only do linear interpolation, but also do smooth interpolation. Okay, so let's go into Excel here. Say we had a range between 0 and 1, and we wanted to generate a line that goes between 0 and some other value. I've chosen 5 to work with. So you can see here, I've generated a series of points that draw out this line that connect straight from 0 to 5. And to generate this line, all we need to do is use our y equals mx plus b relationship to figure out what is the relationship between the horizontal x-axis and the vertical y-axis. We want to get all the outputs here based on some sort of input here. So for example, if the input was 0.5, then we would like to know what is this value here, and we can see that's 2.5. This linear mapping gives us exact control over all the different points we can get on the output based on the input. This is linear interpolation. In this VMK, I'll be showing smooth interpolation, which is shown here. We get a nice smooth transition from our initial starting point all the way up to our ending point. So again, we're starting at 0, 0, 0 for the x, 0 for the y. We're still going to 1, 0, so at x equals 1, we're going to end up at 5. But now, instead of doing a straight line straight through here, we're going to generate a nice curve so that the slope here is 0, and the slope here is 0, and everywhere else in between, we get a nice smooth transition. What we're interested in is coming up with the equation that can generate this curve for us, and then be able to figure out what is the corresponding y value such that it lands on this smooth line. I'm going to quickly step back to show how to generate the equation for this guy, and then we'll take the same principle and use it to generate the equation for this curve here. Okay, so going into Photoshop, for the linear case, we have the x-axis on the horizontal, we have the y-axis on the vertical, and we're starting at a point 0, 0, and we're ending at a point such that over here, this is 1 for x, and we have some other value here for y. I'm going to label it as v. The line that connects these two, that should be a straight line, just imagine it is. We're interested in generating the equation of that line. And we've seen that the general equation of a line is in the form y is equal to mx plus b. For this VMK, I'm going to change m to be a. So we have the general equation ax plus b. First step is to figure out what is a, what is b, so that we have an equation we can work with. Well, let's start off with this point here. We know that 0, 0 is on the line, and it's one of the endpoints. Therefore, when y is equal to 0 and x is equal to 0, what does that give us? Well, we're going to get 0 is equal to a times 0 plus b. If we solve this out, we can see that 0 is equal to b. Therefore, our b in this equation has to be 0. The other value that we're interested in is a here, so we can take the other point over here. We know that the output, y, is going to be equal to our value v when we have x is equal to 1. Subbing that into our equation up here, we get v is equal to a times 1 plus 0. We've seen that b is equal to 0. Therefore, a must be equal to v. Well, there we go. We have our two values, a and b. Therefore, our general equation for this line must be y is equal to v times x, and that's it. Now, just to confirm, let's go back into Excel here, select our line, and let's draw a trend line for it. We want to create a linear trend line, and we want to display the equation of that. And what do we get? Well, we can see that the equation of that trend line, which maps directly over top of our line, you can't really distinguish the two, is equal to y is equal to 5 times x minus 2e to the minus 12. Let's just enlarge this equation so it's a little bit more readable. Minus 2e to the minus 15 is practically 0, so we can omit that. We get y is equal to 5x. And I said that in this example we chose our output to be equal to 5. So our equation matches. Y is equal to 5x is the same thing that we generated here. Y is equal to v times x. Great. So we have a way to generate a linear interpolation for some specified maximum range value. Now let's see how we can do the same thing for a smooth curve. I'm going to sketch out our smooth curve here. We're going to start at 0, 0. We're going to go horizontally, then we're going to go up, and then we're going to smooth out again. If we create an equation y is equal to a times x plus b, we saw that that equation can only generate a line that is linear, so it's only going to be able to approximate this curve in a linear fashion like that. That's not good enough for us. Well, we can try a next higher polynomial, like something like ax squared plus bx plus c. However, if you take a look at the general equation for a parabola, which is this guy here, VMK number 2, we saw that the general shape of that guy is going to look something like this, where we have a nice curve outward, but then it continues going upward. It doesn't come back down. So this doesn't have degree large enough in the polynomial to express this sort of curve. Instead, we're going to have to go a little bit higher. Y is equal to ax cubed plus bx squared plus cx plus d. This is the general equation we need to start with to be able to figure out what is the equation of this line. Step 1. Let's do the same thing that we did before, where we plug in certain values and try them out inside of this equation to figure out what are these coefficients. We're interested in calculating the value of A, the value of B, the value of C, and the value of D. Once we have all 4 of those, then we have a general equation for this smooth curve. Oh, and I forgot to mention, in this example here, we have some sort of set value here that we're aiming for, and this value here, once again, is going to be 1. So we're ranging from 0 to 1 on the x-axis, and from 0 to v on the y-axis. So what do we know about this curve? Well, at x is equal to 0, we know that y has to be equal to 0. Let's plug those values into our equations and see what we get. 0 is equal to a times 0 plus b times 0 plus c times 0 plus d. Therefore, 0 has to equal d, or in other words, d is equal to 0. Okay, so that basically eliminates that one value here. We don't have to worry about it. Let's just scratch it out. What else do we know? Well, let's try the other point. At x is equal to 1, we know that the output y has to be equal to our value v. Let's see if that helps us out. Y, which is v, is going to be equal to a times x cubed, so that's 1 cubed, which in other words is just 1, plus b times 1 squared, so that's going to be 1, plus c times 1, and then plus d, which we don't have to worry about. So we have this equation here, v is equal to a plus b plus c. Okay, well that doesn't get us very much further. What else can we do with this? Well, we know that the slope down here and the slope up here are 0. So let's use that information with this equation to help us solve for a, b, or c. The slope of a line is calculated by the derivative of our equation, so therefore we have y prime is equal to 3ax squared plus 2bx plus c. All I've done here is I've taken the derivative of our equation to generate this equation. So now we can see that the slope of our line is equal to this equation here. Well, I said already that the slope at x is equal to 0 is going to be equal to 0. So let's plug those numbers in and see what that gives us. 0 is equal to 3 times a times 0, so that's going to be 0, plus 2 times b times 0 plus c. Therefore, this cancels out, and that just leaves us with 0 is equal to c. Well, that eliminates c for us, so we can cross that out, and we can cross this out, because we know that c is 0. We got one more piece of information we can use. Here at x is equal to 1, we know that the slope has to be 0. Therefore, let's use that in our equation here. We have 0 is equal to 3 times a times x squared, which is 1, plus 2 times b times x, which is 1, and that's it. We can rearrange this, and we get 3a minus 3a is equal to 2b, or in other words, minus 3 over 2a is equal to b. Well, that's a useful piece of information because we can now use that with this equation to get a relationship between a and v. Let's do that. I'll just scoot this up here. We have v is equal to a plus b, but we know that b is equal to minus 3 over 2a, therefore v is equal to a minus 3 over 2a. Or in other words, v is equal to, well, we have 1a here, and we're subtracting 3 over 2a, which is 1/2 of them. That leaves us with 1/2 a. Well, we're interested in solving what is a with respect to something else, so therefore rewrite this to be a is equal to minus 2v. Great, we're almost there. We have an equation for a, we have an equation for b, and we have the general equation to fill everything else in. So here's our equation for a. We have b here with respect to a, so let's just solve for that. B is equal to minus 3 over 2a. Let's plug a into there, so that gives us minus 3 over 2 times minus 2, leaving us with just plus 3. Okay, so now going back into our general equation, where we had over here, y is equal to ax cubed plus 3x squared, that gives us our equation. For y is equal to a, which is minus 2v, x cubed, plus b, which is 3. Oh, I missed a term here. A is equal to minus 2v, so this should be minus 2v. I missed a v here. We had this part here is a, and this part plus 3v, this part here is b, and then we had x squared. Now we can simplify this a little bit in terms of writing it or programming it, where we could have y is equal to v times x squared all times 3 minus 2x. This and that are the exact same equation, but this one here is a little bit less computationally expensive since we multiply fewer times through. Well, there we go. We have an equation. Now let's compare it with what we have here in Excel. If we go and select this guy and generate a trend line, we saw already that a linear trend line is not going to do the trick for us. I can show you here. The black line here is the trend line. You notice that it doesn't match the curve, the smooth curve, very well. If we go to a second order polynomial, we see that the black line is here, and once again, it doesn't match the curve very well. However, if we increase the order of the polynomial, bam, it lands perfectly on our line, and we have an equation that represents that trend line. So let's enlarge that equation and take a look and compare it to what we generated. Well, we have minus 10x cubed plus 15x squared minus this value here is practically 0 plus another 0 value here. So in essence, we just have y is equal to minus 10x cubed plus 15x squared. Is that what we got here? Well, our v value was 5, so we get minus 2 times 5, which is 10. So we get minus 10 plus 3 times 5, which is 15x squared. Sure enough, that's the correct equation. So what we've just done is come up with an equation that will guarantee that we have a smooth interpolation between some initial value, 0, to some specific value that we can choose. And this chosen value dictates exactly how the shape of this curve is going to look like by this equation here. All we need is to fill in the v value and everything else fixed for us. With this equation, we get a nice smooth transition. If you want to see this interpolation in action, I would recommend viewing the Ghost Toast VMK series, because there I use this interpolation technique quite heavily for animating objects within our scene. If you have questions about this VMK or any other, then I would suggest you go to the forums, and located under the math section, you'll find a math VMK number 10 for this one, where you can post questions specific about this VMK and get all your questions answered.